Welcome to the course Automata and Complexity. We will start with an overview of the content of this course. Computers are based on a universal computation mechanism. What does this mean? Roughly speaking, it means that no other computational model can compute more. Of course, there are practical limitations. Your computer may not be fast enough, you may not have enough RAM, not enough storage space, and so on. But the basic mathematical principles that the computer is based on, the operations that it can execute, are strong enough to compute anything computable. This does not mean that the computer can solve every problem, and that's one of the main messages in this course. There are certain limits to what is computable. Somewhat surprisingly, the concept of universal machines has been invented before computers were invented. Alan Turing has invented Turing machines already in 1936, so almost 100 years ago. Turing machines are an abstract model of computation. They are a simple form of automata that have a read-write tape. And already Turing machines have a universal computation mechanism, so they capture the essence of computation. Anything that your computer can compute, a Turing machine can compute as well. And this means that we can study the limitations of modern computers by studying Turing machines. Turing machines are one of the automata that will play an important role in this course. Next to Turing machines, we will study different kinds of automata. Different kinds of automata have different applications. We will study finite automata. They give rise to the class of regular languages, and one of their main applications is pattern recognition. So if you're looking for a pattern of a certain form in a text document. If you've used programming languages to extract information from text, you've probably come across regular expressions. Regular expressions are equivalent to finite automata. Given a regular expression, you can transform it into a finite automaton. And this principle we will see very often in this course. We have a class of languages, in this case the regular languages, and there's various ways to define this class of languages. You can use finite automata to define regular languages, you can use regular expressions, and you can use regular grammars. And they are all equivalents in the sense that you can transform one in the other. We are going to study also pushdown automata. These are stronger and they give rise to the larger class of context-free languages. One of the main applications of context-free languages and pushdown automata is parsing. So for instance, programming languages are usually defined using context-free grammars. You may have seen Bacchus-Naur forms for programming languages, and this is a context-free grammar for this programming language. And then this context-free grammar can be used to parse this language. And finally, we will study Turing machines. They are the strongest form of automata that we are going to study. They are also as strong as it gets because they are universal. But you should not always use Turing machines. As a rule of thumb, you should not try to shoot sparrows with a cannon. Depending on the application that you have in mind, you should choose the appropriate form of automata. So for instance, if you're trying to extract text from a document, you should really use regular expressions or finite automata. You don't want to start to write a general program to do this. Studying automata is an exciting subject because automata are absolutely ubiquitous. You cannot get around automata in computer science. They are everywhere. Automata stand at the cradle of the theory of computation. They are used in pattern matching in the form of regular expressions, for example. They play a hugely important role in parsing of programming languages. Automata are used in hardware and software design, compiler construction. They play an important role in formal verification and even in mathematics and number theory. So no matter where you're looking, automata play an absolutely central and important role, and therefore understanding the basic principles of automata is absolutely essential for every computer scientist. One of the central questions in this course is, what can a computer do? What are the limitations of computers? And it turns out that some at first glance simple problems are undecidable. This means that there cannot exist a program that always answers these questions, that solves these problems. So no matter how hard you try, it is impossible to write a program that solves these problems. So for instance, this concerns the validity problem in predicate logic. Given a formula in predicate logic, we would like to know whether this formula is valid. We would like to know whether it's always true or whether there's a countermodel. So it would be nice to have a program that answers this question. This would solve many practical problems. Unfortunately, there's a mathematical proof that this is impossible. This problem is undecidable. You cannot write a program that solves this problem. Similarly, program termination is undecidable. So if you start a program, you would like to know whether this program will terminate at some point, whether it will finish its computation. Unfortunately, also this is an undecidable problem, so it's impossible to write a program that answers this question always correctly. So these kind of problems, they are beyond what computers can do. And they will be beyond what computers can do forever, no matter how fast computers get, no matter whether we will have quantum computing working in practice. These problems will remain beyond the scope of computers forever. There's also a class of problems that are decidable, but they are probably not efficiently solvable by any computer. And these are the so-called NP-complete problems. So what does this mean? These problems are decidable. That means we can in principle write a computer program that solves them, but they are not efficiently solvable, so this computer program is inefficient in the sense that we may have to wait for a very, very long time before we get an answer from the program. So for instance, you can think of encryption. If you have an encrypted message, but you don't have the key to decrypt it, but you would like to decrypt the message, then in principle you can write a program that tries every possible key. And eventually your program will find the correct key and give you an answer. But this program is inefficient in the sense that you may have to wait thousands or millions of years before your program finds the correct key. So it's in principle solvable, but it's not efficiently solvable. Two well-known problems in this class of NP-complete problems are the traveling salesman problem and satisfiability in propositional logic. The traveling salesman problem takes as input a number of cities, and we have distances between all the cities. And now the question is, find the most efficient route to travel to all of the cities. In principle, you can try all possible routes, so this problem can be solved, but there is no efficient solution for this problem known at the moment. Satisfiability in propositional logic. So propositional logic, now we don't have quantifiers, we just have Boolean variables that can be true or false. So given such a formula, in principle we can try all possible assignments of the variables. So in principle this problem is solvable, but no efficient algorithm is known. So also this is an NP-complete problem. There is one thing that should be mentioned at this point, namely that there has been extensive research on satisfiability in propositional logic, and there is so-called SAT solvers, that is programs that try to solve this as efficient as possible. And for a large class of propositional formulas, they work very well. So for a large class of industrial problems, SAT solvers are amazingly efficient. So SAT solvers can nowadays solve formulas with 10,000 or more than 100,000 variables, and you get an answer in a reasonable amount of time. So actually SAT solvers have become so strong that for many problems over a finite domain, they are the way to solve them nowadays. So if you have a problem that you want to solve over a finite domain, then you could try to transform this problem into a propositional formula, run a SAT solver, and then interpret the solution of the SAT solver as a solution to your original problem. And in many areas, this is a very efficient approach that outperforms many dedicated solutions that have been developed in these areas over the years. So SAT solvers are very efficient despite the fact that satisfiability in propositional logic is an NP-complete problem. So it just means that there are always some instances of formulas where SAT solvers will have hard times and you will have to wait for a very long time. But for many industrial problems, they are very efficient. So here on the slides we say that these kind of problems, these NP-complete problems, they are probably not efficiently solvable by computers. And this probably hints at the fact that there is no mathematical proof at the moment that they are not efficiently solvable. There has been really extensive research done on this question, and the vast majority of experts in computer science conjectures that these problems are not efficiently solvable. But the conclusive mathematical proof of this fact is still open. And this is actually one of the most important open problems in computer science. It is the question whether NP is equal to P. So we will get back to this question when we study Turing machines. This is a number of typical questions that we will look at in this course. First, we will look at what is a language. And here we are not interested in natural languages. We will not look at English, Spanish, German, and so on. But we look at formal languages, programming languages that can be understood by computers. When we look at languages, there are two main aspects. We have the syntax and we have the semantics. The syntax describes the form of the words in the language. And the semantics describes the meaning of these words. In this course, we will purely focus on the syntax of the language. We will not be interested in the semantics. Next, we will look how can languages be recognized, how can they be defined by computers. And we will use automata, we will use grammars, regular expressions, and so on. We will look at different types of automata on what kinds of problems they can solve. We'll look at finite automata, push-down automata, Turing machines, and so on. And finally, we will look how much time and memory is needed to compute, to solve a certain problem.